Eastern Ghats of India. Siva Prasad and Professor Venkateswara, I think.
Yeah.
Venkateswara Rao.
Sir, am I audible?
Yeah, sure.
I only request the participants to adhere to the timing.
Yeah, true.
Not
Correct.
to go beyond the timing. Thank you.
Yes, sir.
Okay, sir.
Thank you, Professor Mathur. Yeah.
Okay. So this is, I think this presentation is about 15 minutes, if I am not wrong.
Yeah, right. Correct.
Yeah. Thank you, sir.
Talk. Yeah, please.
Yeah. So I thank the organizers for giving me this opportunity for presenting our work. My scholar Siva Prasad is also, I think, online. And this is regarding the IP survey on kaolinised zones of chondritic terrain. Let us in the Eastern Ghats of India. Next slide, please. You can see on our right the lithological subdivisions of the entire Eastern Ghats. It constitutes chondrites and then charnokites and other transition zones, alkaline complex and so on, in which we have a small red spot, KRSB, Kandivalsa River Subbasin, which is again highlighted in the corner of this window. That is near Chiprupalli, this entire area in Vijayanagaram district of Andhra Pradesh. And this basin is completely constitutes of mostly, chondrites, and of course a little bit granitic spots and other quartzite and so on. So in this, we have conducted our surveys. We have been doing it for quite some time. And let us have a next slide, please. Yeah. Let us try to understand the various concepts that are given by our elders, starting from Fermer and then Prabhakar Rao, Krishna Rao, and then these are the regarding the geology, its origin. Basically, the chondrites are sedimentary in origin, but they got metamorphosed and became hard rocks. And then in a due course of time, they got it weathered and fractured also, because the tectonics also are applying. It is the Eastern Ghats mobile belt. So the typical chondritic rock consisting of sillimanites, garnets, feldspars, and the quartz. When these minerals are got weathered, it produces something like a kaolinite. And probably the first time the Mahadevan, the legendary figure in our geology, was the first scientist to postulate hydrological concept of this region, and has pointed out that due to the action of water, the chondrites are altered in two different manners. On the surface, the rock changes into a lateritic soil. Then in the subsurface formation, when acted upon by the water, alters itself into the kaolin. That is what the kaolinization is there in almost every part of this chondritic terrain. Next slide, please. Yeah. Sharma, our guru to our hydrological sciences, has conceived 4-layer system in the chondritic. That is the top soil zone underlined by some talus zone, particularly in foothill areas, which again in turn into underlined by a weathered kaolinized portion. So earlier work has confirmed very much there is a kaolinized portion, and later investigation by our group has brought out that in this land, flat uplands are more yielding in terms of groundwater, and beneath the streams, the chondrites must have transformed itself into a kaolin. It is a kaolinization more beneath the streams. And then when the water is flowing as towards the mainstream, in the flat uplands, it is getting accumulated, because beneath the streams, it is almost like a dike-like thing. The kaolin is obstructing. So this kaolin is acting as a barrier, evidently preventing lateral movement of groundwater towards the stream. So near the streams, the wells are low yielding. It is noticed that as the weather depth increases, there is a greater chance for the formation to divide of water. The more and more kaolinization occurs, the less and less water it comes. Survey of failed wells in certain areas of chondrite terrain has revealed a strong relationship between the failure of well and then kaolinization of the certain pockets. So particularly in certain pockets, the kaolinization is more. Normally in earlier days, in 80s and 90s, we have had only a small resistivity meter. We used to conduct soundings and then interpret the sounding and then drill the well and so on and so forth. But some of these things, sometimes we used to mislead with the sounding curves, because they are giving the same kind of picture, whether it's a high yielding or low yielding. So then we have to resolve this. We have conducted 2D resistivity, 3D resistivity, IP, so many things. In this case, we are presenting only IP and on. Next slide, please. So, next slide. Yeah, this is the concept what we try to put forth before you. You can see the weathered and fractured chondrite is there, and also kaolinized portion above it. This kaolinized portion is varying in thickness. At some places it is very large, at some places very small, and then there the weathered portion is more. Suppose if your well happens to fall on this large kaolinized thickness, no yield, very less yield rather. And if you fall in a fractured portion with a little kaolinized thickness, then the well yield is more. This is the conceptual model. Next slide, please. This is in field where if you see the white is portion there, garnets are also there. It's a part of the chondrites formation. So when you are drilling, actually sometimes it is very difficult to drill when it is fully kaolinized. The drill bit got stuck in the hole. That is how the kaolinite behaves. Next one. Next slide, please. Yeah, this is what I was telling. I have selected 3 places. One is at Sivaram near the road. Another one is Sivaram near the stream. Another one is Kondasammam. These are the villages. These are the pairs of wells. Yet with very little distance, one well is got no yield, another well got a high yield. But almost you can see with 1D resistivity soundings, you get a similar kind of interpretation. So to resolve this, we have gone for this kind of various kinds of survey. One among them is this IP survey. Next one, next slide, please. Yeah, just for a recap to our textbook knowledge, you can see the IP, how the phenomena occurs. You can see in the top right portion, the right-hand corner, the ore body, suppose if it is there, when we apply a current, that is a full line is applying our current, normally plus minus develops to the ore body. And when switch off your current, then the dotted line that acts as a battery, and that's how the residual current will act. In a graphical form below, you can see this applied current is VP, and then residual voltage, that is when you switch off the residual voltage, the VT, then you simply you can show in the form of a curve. So VT by VP is known as chargeability in IP survey, and in some systems the decay is registered over a length of time. Then it is millivolts seconds per volts. So the chargeability can be expressed in milliseconds and so on. Next slide, please. Yeah, this is to show that the membrane, there are many kinds of polarization type thing. Membrane polarization is also called electrolytic polarization, and then electrode polarization. Basically, the difference is the polarization occurs in the interface between a non-metallic like clays and all, and the fluid. Then that is called membrane polarization, or and also called electrolytic polarization. And then metallic minerals between the disseminated earth surface cause electrode polarization, whereas membrane polarization usually associated with the clays, whereas electrode polarization is usually associated with the metallic minerals. So in contrast, electrode polarization is produced because of conductive minerals in the host rocks, where the electric current flows in partially electrolytic and partially electronical. So there are 2 or 3 phenomena there, and they try to produce this polarization and then try to give the residual current. Next one, please. Next slide. There are many people earlier, they have conducted this survey, IP survey. So basically, as alteration of rock by the weathering of alumina silicate minerals, feldspars, mica, or other clay minerals lead to the formation of kaolin in the subsurface. Basically, under humid and subtropical conditions, kaolinization is strongly manifested in the formation of kaolin as a result of weathering in granites and other almost all feldspathic rocks. In this process, finely flanked alumina-rich mica is initially formed from the feldspar. So that is how kaolinization formation is there. And when this clay formation is there, there is a polarizability. So for this clay and associated minerals, one can apply successfully these IP surveys. There are many other workers, as you can see. The dependence of polarizability of soils favor the application of IP method. So Telford and Sharif and many others, Slater, they have given their opinions The electrode polarization is greater than the membrane polarization depending on the presence of metal minerals and rocks. Okay, of course, resistivity surveys is more popular in groundwater investigation, but sometimes, what will happen, for example, in a sandy sedimentary formation, a low resistivity anomaly can be caused either by an increase in ion content in the water formation or a higher clay content. So that time the resistivity may a little bit difficult to interpret, but the chargeability of the formation can be distinguished, such as low resistivity anomalies and so on. Okay, the IP method is not to determine the type of rock, but this method is used to know the amount of conductive minerals. So from found in the rock. So the presence of clay interacting with groundwater may induce IP effect and minimize the resistivity. The impact of clay decreases the resistivity value and increase the value of chargeability. This is the concept on which we have tried to map the chargeability 2D imaging. The next one. This is what the instrumentation used. This is ABM's terameter SAS 1000, a multi-electrode, two-dimensional. We can do it, signal averaging system. We have very closely failed well and successful, hardly around 150 meters apart. There are 48 electrodes, 3x16, using Venner-Sumbacher configuration. And you can see we can measure in a time, over a period of time, we have measured this thing, the voltage. And of course, these are all known things. I need not do in the imaging system how we take measurements. The next slide, please. Yeah, this is at a Sivaram village near the road. There is a upper figure is for the successful upper images for successful one. This is a chargeability. You can see where success well is located. There the chargeability is around 3.58 milliseconds. And in just around 150 meters, we have another failed well. You can see the clay mineral dominance is there. And you can see the chargeability is of the order of around 40 meters, 0.3 milliseconds like that. So this is the difference. The more the kaolinization, the chargeability is coming less. And if it is relatively weathered and not so much kaolinized, chargeability is somewhat medium. And if it is for the higher basement rock, chargeability is coming more. Okay, next one. Next slide. Yeah, this is another pair of Sivaram village near the stream. Actually, here the upper surface is very disturbing because quartzite rock is on the surface. That's why the error came very large, and that's why distinction became very less. But even still, here also, and the chargeability in the success well, where it has penetrated through the fractured zones, it has a little bit more compared to the failed well, less, mostly dominated by clay mineral dominance. Then we go to the next pair, please. Next pair. Yeah, this is a Kondasambam village. You can see here clearly the error is very less, and inversion is very good. So the chargeability at the success well, where this formation is weathered only, not so much kaolinized, it is around 1.43 to 2.63. It is coming. Whereas for failed well, the chargeability is of the order of around 0.235 or something like that. So now with these three things, we can compare. Next slide, please. Next slide, please. These are the depth range and chargeability values at all the success wells. If you just look at closely, because in the map, a little bit approximate, we have measured it. And in the first well, Sivaram village near the success well, Sivaram village near the road, success well, weathered rock saturated with water, chargeability 3.58. And because as I said, there is a lot of error in the second pair. So that, but definitely in the second pair also, weathered rock with saturated water is more than 1.07 chargeability. Well, you can see in the Kondasambam village, weathered rock with saturated water, that is 2.63 to 3.73. So the upper layer, when you compare to upper layers, kaolinized layers, chargeability is around 0.33 to somewhere around 0.16 like that. That means chargeability is less in the highly weathered chondritic formation, which has become kaolinized, whereas the chargeability is medium that is around 2.6, 2.632, 3.7, something like that. But when it goes to basement rock, it is much higher, even going up to 6.1, 6 point something. So you can see the more weathering may become kaolinized means chargeability is less. Medium weathering, or when it is saturated with water, the chargeability is something 2 point something like that. And if it is occurring with basement rock, much higher chargeability. These are some of the things we have observed. Next one. Next one, please. Yeah, this is with regards to failed well. The most characteristics of failed well is the kaolinization depth is very high. You can see the kaolinized layer depth is 30.14 in the first well, and then second well also 36 point. The entire almost the entire aquifer has become kaolinized. So that is why we can really conclude from this kind of investigation that with medium chargeabilities of around 1.7 or 8 to around 3. This is a weathered formation without much kaolinization. Suppose if the kaolinization occurred, the chargeability is less, and also thickness also is a very high when kaolinized is occurring. Thickness of the kaolinized layer is high. That is how the failure of the wells occurring. Next one, please.
Mr. Venkateswara Rao.
Yeah,
please.
Yeah, this is the one based on this knowledge. We have very nearer to that, because very closely the wells are failure and success are occurring. Again, very nearer we have drilled another well, which is reasonably successful well. Moderate chargeability we have observed there. There are around 2.11, something like that. We have drilled, and that was have given a medium yield. So this kind of knowledge can be used for locating the highly kaolinized zones, and that way we can use this knowledge. Next one, please. I am concluding, sir, almost. Yeah. Depending upon the pore geometry and degree of saturation, the large difference in potential decay with time is observed between the success and failed well pair, sir. The chargeability in the subsurface is varied at success and failed well. So, okay, all these things we have observed. The IP strength at clay mineral concentration is by the membrane polarization mostly, indicated with low chargeability, and it is higher as weathering decreases due to electrode polarization. This is the one important thing that we take a home point. And of course, if the thickness of this weathered zone is high, I mean highly weathered zone, highly weathered quantity is high thickness, then wells become automatically failure. And the aquifer thickness is more, that is between the chargeability of around 2.63 to 3.8, and the thickness of that weathered fractured zone